Okay, so hello everybody, and welcome to a seminar where we've got, I think for the first time, quite a few people from CESAC here. So this week we'll be hearing from Patrick Hoover, who's the director for the Center of Neutrino Physics at Virginia Tech. And as well as being interested in fundamental physics, I think he also has interests in the nuclear security, those kinds of more applied fields. And so we're going to hear a bit about some of that today. So Patrick.
Thanks for the nice introduction. Thanks for the invitation. As we've sort of discussed in this pre-talk band, it would be much nicer to be there in person, but that probably has to wait a little bit. So yes, this talk is titled Dark Matter, Neutrinos and Nukes. It's based on this preprint, which you can find there, and it was done in collaboration with Coxwell, a research scientist at Virginia Tech, and a poor girl, which is an undergraduate. She was an NSF RU student last summer here at Virginia Tech. All right, so let's start with the early history of the neutrino. This, of course, is a very famous letter written in 1930, where Pauli proposes the neutrino. It starts with Liebe radioaktive Damen und Herren, and goes on to essentially, because of angular momentum conservation and energy conservation, to postulate a third electrically neutral particle in beta decays. Shortly thereafter, Fermi developed the theory of beta decay, and based on that, Bethe and Piles estimate the detection cross-section to be somewhere in this 10 to minus 43 square centimeter order, where the neutrino energy is measured in MeV, and not surprisingly conclude that the neutrino is practically invisible. So they fundamentally assume this particle never can be detected. And this is something which bugged Pauli. So Pauli is supposed to have said that he's really unhappy about that he's proposed a particle which cannot be detected. And so then what the first real serious consideration of neutrino detection happened in 1945 by Bruno Pontecorvo, where he proposed, at that time he was working at Chalk River. He proposes radiochemical detection. And this is a copy of this. Is a 2-page paper, it's very short. This paper promptly was classified by the Atomic Energy Commission because of the potential for detection of nuclear submarines. But what he proposed really was, you have chlorine-37, you have a neutrino interacting with that, which produces argon-37 and the electron. You would not observe the electron, but you would sort of chemically separate the argon from the chlorine. And I think there's a reason Pontecorvo stumbled across this one, because even a particle physicist, a nuclear physicist, knows enough chemistry to know that chlorine is a halogen and chemically very active, and argon is a noble gas, which makes it chemically inert. So it's chemical separation of these two is sort of trivial. So it's chemically then separate the argon-37 and wait for it to back decay to chlorine-37, and you would observe the back decay, and that way would count single atoms of argon-37. And so you still have to try to beat 10 to the minus 42 square centimeter if you try to detect the neutrino. So you get a 10 to the 24, so from Avogadro's number. That leaves you with sort order of 10 to the 18 neutrinos. And of course, to get 10 to the 18 neutrinos, you need 10 to the 18 beta decays. And the way to do this is to get this from fission. So if you want to get that number of nuclear reactions, you need to basically have a macroscopic quantity of stuff undergoing a nuclear reaction. You cannot really use an accelerator very easily for that. But in nuclear fission, you have a self-sustaining chain reaction, which eventually will fission macroscopic quantities of material. And as you can see, this here sort of is a schematic of the fission process. You have a neutron splitting uranium-235 nucleus into 2 pieces. And traditionally, barium and krypton are shown, I think, because barium is the thing which Hahn used to identify this reaction. You make a few more neutrons, and if you do this right, these neutrons released can induce further fissions, and in that way you can fission large quantities of material. This diagram does not contain any neutrinos. The neutrinos are not made in the fission process. What's shown here in the upper right-hand corner is sort of a snapshot of the chart of isotopes, where the neutron number increases to the right and the proton number increases from bottom to top. The black squares are the stable elements, and the colored region encodes the distribution of fission fragments. Fission is not a deterministic process, it's stochastic, so you get different fragments in each fission process. And you also can see it's isometric, so you have a heavy peak of around 140 in atomic mass, and you have a light peak at around 90 in mass. And then if you look at this closer, you would find that on average, you're about 3 steps away from a stable element in this lower peak, and the same is true for the upper peak. So you make 2 fragments, which have to go 3 steps to become stable. Well, each step is a beta decay, so you have 6 beta decays per fission, so you get 6 neutrinos per fission. Or in units which in this context of the small cross-section maybe are more relevant, you get about 10 to the 24 neutrinos from fissioning 1 kilogram of uranium to 35. And so a nuclear reaction, nuclear chain reaction would be the ideal place to give you enough neutrinos to have a chance to detect this. This was the first, and Pontecorvo did not follow up experimentally. So in the 50s, Cohen and Reines proposed this here to get approved. This is a sketch taken out of the lecture notes for the Reines Nobel lecture. And as you can see, the proposal was you put a nuclear bomb on top of a steel tower, and you have here this detector falling in an evacuated tunnel and registering the neutrinos. And the evacuated tunnel was to protect it from the ground shock. And here we then have feathers and foam rubber, which would sort of collect the detector maybe in one piece. What's interesting is A, this proposal strikes us as very odd. B, it actually was approved. They got the go-ahead. But this all is not so odd if you consider that their day job was to instrument atmospheric nuclear tests. And they didn't propose to set off a nuclear bomb to discover the neutrinos. What they proposed is at an already scheduled nuclear test to add this piece of instrumentation. And that's the thing which was approved. But this is, of course, not how the neutrino discovered. This is how they were really discovered. And they exploit here, so they use the reactor. In this case, it's the P reactor at Savannah River. Here, that's here in the background, which, by the way, was a plutonium production reactor, so also related to nuclear weapons. And this is a sketch of the detector, so the dimensions are roughly so 1.50 meters by 1 meter or so. And the idea was to use this delayed coincidence reaction. So what you have is the neutrino comes in, it makes a neutron and a positron. When it hits hydrogen in the material, the neutron wanders around for a while, gets captured in, for instance, cadmium we've put in the detector, which then makes gamma rays, you can see. And the positron basically stops via ionization, deposits energy, and then gets annihilated and produces 2 more gammas. The trick is that the positron process happens promptly, whereas the neutron capture time scale is a few microseconds. And so you first get this prompt signal, and then you get the delayed signal. With that, the background can be reduced to the point that the sort of steady flux from a reactor can be used instead of the nearly instantaneous flux from a bomb. And it's really this reaction principle and also essentially detector design, which has been used for all reactor neutrino detections to date. And this was achieved in 1956. So now we're moving on to solar neutrinos. Turns out that helicity allows the chlorine-37 reaction only for left-handed states, so it cannot happen at reactors. And so this is really different from the Majorana neutrino-antineutrino question. This is a helicity question. The sun is a neutrino source. And so in 1960s, Ray Davis built a solar neutrino experiment at Homestake using Pontecorvo's chlorine-37 reaction. And here, Ray is not swimming in the chlorine solution. This is the water shield of the detector. You see this tank here in the background, that's what contains the chlorine. And so what you do is, as I indicated earlier, you chemically extract the argon-37, and then you detect their back decay into chlorine-37 on a 1-by-1 basis. And the half-life of argon-37 is around 30 days. And this is a crucial requirement, because if it's much, much longer, then you don't see the back decays because you have to wait forever. And if it's much, much shorter, then you would have to do the chemical extraction much faster than you can do it. And so 30 days is sort of a sweet spot for a solar neutrino experiment. Now, can we also achieve passive detection of reactor neutrinos? And we would need inverse beta decay for that. You need a small Q value, so you don't want to have a large threshold, and you need a large matrix element in the nucleus for this to happen. Or in nuclear physics speak, that would be a small log FT. And the half-life needs to be sort of in between weeks in decades. And so what you can do is you can compute the rate of inverse beta decay and inverse electron capture, which is sort of a similar reaction where a photon is sort of some electromagnetic interactions involved. But what's important is you can do this for all isotopes in the chart of isotopes. And what you then find is that here is the free proton. This is what Cowan and Reines used. And then you see the only thing close on a log-log plot is helium-3. Everything else is 2 or 3 orders of magnitude down on this figure. And of course, you see the vertical axis is truncated, right? So nothing in this direction really goes very high. So practically, you're confined to helium-3. And what you could do is this inverse tritium decay reaction. We have helium-3 plus an anti-electron neutrino becoming hydrogen-3, which is tritium and a positron. And you would wait for the tritium back decay. Again, here, separating helium from hydrogen would be easy chemically. But the problem is that the half-life for this reaction is, for the back decay, is 12.3 years. So you would have to count for 12 years to get 68% of your signal. So that maybe is not terribly practically, but the real showstopper, of course, is that helium-3 is really exceptionally rare and expensive. So you're talking about a liter of helium-3 at standard atmospheric pressure, that's a gas, a couple of $100. Okay, so getting a kilogram of that stuff is fundamentally not possible. And so having done this exhaustive search through all 8,000 isotopes, the conclusion is that a charge current reaction, that is where proton and neutron change to nature, will not work for passive neutrino detection at reactors. So in the meantime, in the real world, all sorts of things happened. And so just sort of as a quick reminder, this is Castle Bravo, the first sort of deployable nuclear weapon, thermonuclear weapon, I should say. Then here we have the Cuba Missile Crisis. We also had Sputnik, which really is relevant in the context of ICBMs. And of course, you had the building of the Berlin Wall, which sort of was a very tense phase of the Cold War. And from that, we can then sort of look at the global nuclear warhead stockpile or the inventories. And you see this starts here, really takes off in the 50s. And you see here the US stockpile goes like that. The Russian stockpile came later. You see, on that scale, all the rest of the world is just a blip at the bottom of the scale. And we had a peak sort of in the mid 80s at 70,000 or so. And we have come down from that very high number considerably till today, but it's still more than 10,000. And at the same time, of course, 10,000 warheads of 2020 design are probably a lot worse than 20,000 1960s warheads were in terms of their capability to inflict damage. So this is the problem which is still with us. And how can we try to control this? One of the fortunate facts of nuclear physics is that there really is a very limited number of isotopes which can maintain a fast neutron chain reaction, which you need for a nuclear explosion. These are the 3 only practically relevant ones. It's uranium-235, uranium-233, and plutonium-239. And by looking at their half-lives, you immediately know that only uranium-235 can occur naturally, and it does so with a small sub-percent natural abundance. And of course, these other 2 cannot occur naturally because they have decayed away since the supernova, which gave, produced the ashes out of which the solar system is made. And the critical masses for these things range between 50 to 10 kilograms. So you need kilogram quantities to do this. So how do you get those things? Uranium-235 occurs naturally, but needs to be enriched. So this here is centrifuges. And this, by the way, are not Iranian ones. These are the European ones. This is a picture of a Urenco facility. Or you use a nuclear reactor. And what a nuclear reactor really does, it does what the alchemists always dreamt of. It really is transmutation of elements. You transmute either thorium or natural uranium into uranium-233 or plutonium-239, and you do this inside a nuclear reactor. This is a picture of the Hanford B reactor, I think. And so the fact that these materials are rare and difficult to obtain is what gives us a fighting chance to contain nuclear weapons. And based on that realization, a number of treaties exists which create the legal framework to try to control this problem. Of course, the still most crucial one is the Nuclear Non-Proliferation Treaty. It bans the acquisition of nuclear weapons by non-weapon states. It also bans transfer of knowledge regarding nuclear weapons. and it commits weapon states to disarm. And what's special about it is it's verified by IAEA, which is the International Atomic Energy Agency safeguard. So it has a verification regime in it. It entered force in 1970. Then we have the Comprehensive Test Ban Treaty, which has not been ratified, I should say, but it bans all nuclear explosions in all environments. It does have a verification regime, which is the IMS, which is seismographic, and the CTBTO, which, for instance, has infrasound sensors and so on and so forth. And so this treaty came some 20 years later. And fundamentally, nuclear testing in most countries really has more or less come to a halt around that time. Then you have also another attempt, a more recent attempt at sort of constraining this problem is the PMDA, the Plutonium Management Disposition Agreement, where basically Russia and the US commit to dispose of 34 metric tons each of weapons usable plutonium. And that's already been declared excess to the military needs. So this is really stuff they don't need. This is currently suspended. And certainly the technical implementation in the United States has hit various roadblocks, even if it were to proceed. And then most recently, we have the Treaty on the Prohibition of Nuclear Weapons. And so this really would be a global nuclear weapons ban. And so what does the IAEA do? This is in a nutshell trying to describe the complex mission. I don't want to go through each box on this slide, but maybe what's important here is their annual budget is sort of 140 or 150 million a year, and it's about 1,000 people doing this. Okay, so it's not an enormous entity. And any part of the US government far exceeds this in budgets and personnel. And that even the NSF is much, much larger than that. Okay. And so here this gives you an idea how safeguards fundamentally work. They go to a site and then they check the cameras, they check the seals, they check the spent fuel pond, they do a lot of accounting work, and then once they've done that, they have had a sort of 8-hour workday at the facility. This is how this works. They have very limited time. And the reason for that is if you look at this here, so they conduct nearly 3,000 in-field verifications. They verify 25,000 seals. They collect 1,000 samples. They look at 2,000 satellite images. It's just an enormous number of things they have to deal with, since they, of course, cover 184 states and 1,300 nuclear facilities. So they have very little time and a very limited budget. All right. So now this brings us back to neutrinos. Okay, so neutrino reactor monitoring. This here is picture of the Rovno detector, which actually collected this data here to the right. This was first proposed by Borovai and Mikelian in 1978. And swiftly they followed up with building this little detector here, which is a very nice piece of equipment. And in the 1980s, they started taking data. This again is based on inverse beta decay. And you see the data here. So on top, this are the counts per day you had with this little sort of washing machine size detector. And you clearly see how this correlates to the bottom plot, which is the reactor power, which is measured by the operator of the reactor. And you see that this data is very highly correlated. And as I said, this was based on inverse beta decay, and the long line of detectors followed in the US, Songs, France, Nucifer, Japan, Panda, Vidar in the UK, Chandler in the US, iDream in Russia, Imran in India, and so on and so forth. And so people have been building these sort of smallish type neutrino detectors for monitoring reactors since then. What happened sort of in the last 3 years or so is so we wrote this paper here in 2014 showing you how well you could do monitoring the plutonium content of the Iranian IR-40 reactor. And so if somebody took out the reactor core during a period where it didn't have safeguards access, you could find the missing plutonium within a week at very high confidence. And so we wrote this in 2014, at which point no detector existed which could do this measurement. In 2018, neutrino detectors basically reached a point where they could work at the surface and actually would have been able to be used in a case like this. This here is a picture of the Prospect detector, which is one of these detectors which could do this, uses liquid scintillator, and liquid scintillator can and does leak. They had a leak and had to dismantle the detector as a result. Here's the Chandler detector, and for full disclosure, this is a Virginia Tech development, which uses plastic scintillator. This is a very small device, as you can see. This is a chair for comparison. But the point is that if you scale them to the size you need to do this here, you're still talking about $1 million ton scale devices. And that in itself indicates that they're not great fit for the IAEA. It has nothing to do with them, not working or not being otherwise maybe suitable, but it's just that they're too expensive and too big. Next on to CEvNS, which is coherent elastic neutrino nucleon scattering, which is, this should be nucleus, I'm sorry. And the idea is, so this is the cross section. What's really important here for this purpose is there's a factor n square, and this is the number of neutrons in there. Since it's a coherent reaction, it does not scale with the number of neutrons in the nucleus, but it scales like the square. And since you can have up to 100 neutrons or so in a nucleus easily, this is as large, maybe 10 to the 4/10 enhancement. And so that's why people are interested in this. And so how this looks schematically, neutrino comes in, it scatters off the nucleus, neutrino still leaves with some residual energy, and the nucleus gets a recoil. And then the task is to detect this nuclear recoil. And that's really what sort of the bulk of this talk is about, detecting nuclear recoils. And despite the fact that you have this n-square factor, since this cross-section peaks at low energies, turns out that to achieve the same event number per unit mass than an IBD detector, you need very, very low thresholds. If you go through sort of the mass ranges of things, the thresholds have to be well below a kilo electron volt. And this is a very technically non-trivial requirement. I should point out that this reaction has been observed for the first time in 2017 by the coherent collaboration at this Spallation neutron source at Oak Ridge. These are fairly high energy neutrinos compared to reactors. These are 50 MeV neutrinos. Reactors make 4 MeV neutrinos, and so as a result, the detection of reactors is still an outstanding and unsolved problem. All right, so now to the concept of the...
Maybe you mentioned this
yes.
already, I missed it, but is the detection of CEvNS purely for intellectual curiosity, or are there any fundamental property of neutrinos that you can
okay, very good question. So I think, first of all, the first driving reason was intellectual curiosity. But once you go beyond this first discovery, what can you learn by it? So for instance, you can measure the weak mixing angle at very low energies and see whether there are new states showing up at that, for instance. You can test neutrino magnetic moments in these experiments because they sort of interfere with this set boson exchange. You can look for non-standard interactions. So if you had a set prime, for instance, there are some versions of low energy set primes where already the coherent experiment puts better bounds than anything else. So it's really very sensitive to low energy new physics. For nuclear physics, it's interesting because you can, for instance, measure the neutron radius of a nucleus, which is very hard to measure otherwise. And has been so far measured really only for lead at Jefferson Lab using parity violating electron scattering. And you're very sensitive to this in this type of reaction. So there's some real science to be done with that. The other thing I should say is this is a background for dark matter searches. Solar neutrinos doing this in a dark matter detector looks exactly like dark matter. And in supernovae, this is a very important reaction to determine the neutrino opacity and therefore energy deposition. So it was important to confirm that this reaction exists like predicted.
Thank you. Could I ask one more question? Do the protons play any role in
No, not really. The reason is that if you compute the weak charge, and given the value of the weak mixing angle by accident, the proton has nearly no weak charge. It has 1% of the neutron's weak charge, and so far fundamentally doesn't count for this exercise.
Thank you.
All right. So now on to our concept here, and it's really not our concept, to be very clear. But the concept is that the nuclear recoil eventually damages the crystal lattice, and it can do so permanently. And the two types of damages you can have, you either form a track of damage, or you just form vacancies by knocking out atoms of their lattice sites. That means this damage in the crystal lattice allows for an in principle offsite readout of the detector, and so the detector is passive. And that's a really crucial requirement for what we're talking about. And you have an intrinsic rejection of ionizing backgrounds if you choose the right crystal, and then you would have as only remaining background neutrons, which is much better than if you have to really deal with all gammas and betas as backgrounds. And this has been amply explored for dark matter detection. There's a long list of paper. I hope I got the chronology right and did not forget anyone, but notably, of course, there's a whole range of papers Sebastian here was part of. And it really was the seminar that Sebastian gave shortly after one of the first ones he appeared at Virginia Tech, which sort of put me on the scent of that idea. And so what you see here, this is a simulation with TRIM, and I'm going to talk about this a little bit more on following slides, but this is essentially a tool where you can try to simulate what happens in the crystal. This sort of is 20 nanometers by 12 nanometers, and each colored line is a track, and each dot is a vacancy if made, and these are 50 neutron events which we put on top of each other, and these are atmospheric neutrons. And we put 57 events from a reactor next to them. And you see the neutrons look different than the 7th events, but both of them do make events. And so the task or challenge now is, we think we fairly well understand how these things are formed, but how do you actually know that they have formed? So how do you detect them, all right? And so that's what we're gonna be talking about here going forward. So solid state nuclear track detectors are not new. So the idea is that crystal damage tracks from multi-MeV events can be seen by you etch fundamentally the crystal and the area which has damage. So the lights turned off here. To etch much faster than the surrounding because their damage and the bonds are not as strong. And this here is, for instance, shown. This is, I think, a fission event in mica. And you see here nice these damage tracks. And the size here in this case is sort of 10 microns or so. This has been used in naturally occurring mica, for instance, to put limits on magnetic monopoles, but it's also used in specially made plastics for radiation detection, as a matter of fact. So tracks versus vacancies, damaged tracks, as I said, result from the distortion of the crystal lattice and in response to ionization. And so you have then strain. So if you look at an insulator and you displace the electrons from the lattice sites, they cannot move back. And so you have basically frozen in this charge imbalance. And that puts tension into the crystal, a strain into the crystal. And it's this strain which weakens the chemical bonds, and then you can exploit that for imaging. Vacancies, of course, are point defects in the lattice. You're just taking out really literally an atom out of its lattice site. And for many materials, these things are persistent at room temperature. And generally the rule is if they have a melting point more than a few hundred degrees centigrade, they probably will have stable defects or tracks at room temperature. So to give you an idea how these things go, so here on the left-hand side, we have count the vacancies each neutrino makes, and these are reactor neutrinos. And you see you get a fraction of events which leave no vacancies, some which get 1 vacancy, some which get 2, and so on and so forth. And for comparison, you see here to scale the background from atmospheric neutrons, which clearly is larger. But I should say in neutrino business, only by an order of magnitude, which is absolutely excellent. And you see they also have a much flatter spectrum. They don't fall as steeply. You can do the same thing for tracks where we measure the track length. You see the track length spectrum falls also very steeply, even more steeper than the vacancy spectrum. And you have the same effect that the neutron track spectrum is sort of flatter in this distribution. And so that the signal to background is still a factor of 10 roughly in both cases. What you also do observe, however, is that the tracks longer than 2 or 3 nanometers are basically vanishingly rare. And so you really need to be able to do nanometer scale tracks well to have some efficiency if you want to use this for reactor neutrino detection. And so I want to briefly talk a little bit about the physics of vacancy formation because it's non-trivial, and certainly was non-trivial for me when I started to learn this. I'm sure every particle physicist coming to that thing has to do some reading before you can do this. And so maybe this is interesting to you. So how this basically goes is, so you have these sort of even in thermal equilibrium, we have that the lattice atom gets displaced from its site, and then you have a hole and the so-called interstitial atom, which are attracted by Coulomb interaction, and they form a Frankel pair. And these Frankel pairs recombine very, very quickly due to the Coulomb interaction, also due to the lattice strain, which basically wants to push them back. And to really get a permanent vacancy, you need to separate them far enough that basically the screening inside the crystal can effectively screen the Coulomb interaction. And so the interstitial no longer can feel the presence of the hole and then starts to wander off because the random chance of falling back is very small. Formation of permanent vacancies is really one of the main mechanisms for radiation damage in high radiation environments like a reactor vessel in a nuclear fusion or fission reactor. And we use this TRIM package, which is a so-called binary collision code, which essentially is playing billiards at an atomic level, with the difference that you're not having a hard scattering potential, but correct interatomic potentials to compute the cross sections. And so what you can see easily here is that in some directions in the crystal lattice, the displacement energy or threshold displacement energy is very high, whereas in other directions it's lower because you're not running immediately into something, right? And so this is clearly a spatially directionally dependent effect. And here you see a whole range of measurements in copper in this particular case. And you see here in black a simple theoretical line. This is more or less what this TRIM code implements, and the measurements on a log scale are not infinitely far. That's maybe what I want to state. What's important in our case is really the lowest energy at which these vacancies occur. And you can see it's not sharply this threshold damage energy, but some of them do occur below. So it's a soft transition, and that's really what we worry about. So the threshold displacement energy is a key quantity. It's crucial input to these TRIM calculations. It's actually really hard to measure. Data does exist mostly for metals or stuff which is used in nuclear engineering, but empirically it's found to scale with the melting point. And this here are the measured values of the threshold damage energy of a whole bunch of elements, plotted as a function of density times melting point. And you see they follow a nice, sort of follow a nice fit. Okay, so this heuristic is not super accurate, but gives you some idea. Okay, and we use this heuristic to obtain values for the threshold displacement energy for materials of interest to us. And we have to acknowledge that there's some real uncertainty in there. But I'll show for some of the results how they depend on the exact value of the threshold displacement energy. And if you're not off by a factor of 3 or so, then our results are probably fine. So here's a nice test case. It's calcium fluoride, which is not something we're interested in this study, but has been studied in great detail because there's a proposal to use this for neutron dosimetry at very high fluences, like inside a reactor. And the idea is that basically you make enough vacancies that the crystal changes its size and responds, and you measure the size change, change its density, and as a result changes its refractive index. And you measure this refractive index remotely with a laser beam, and that would be attractive. And so the step up from TRIM in terms of computations and simulations is molecular dynamics. In this case, they used this LAMS code developed at Sandia. And this shows you a picture. So here you start off and you see how here the crystal lattice deforms and bounces back and does stuff. And here you see at some points this black dot, which is the interstitial. And in green, you end up here with the one interstitial fluorine atom in this run after sort of 3 picoseconds. First of all, these calculations show you a really strong anisotropy in the threshold damage energy. So it can be 5 times higher in one direction than in some others. But if you look at the spatially averaged threshold damage energy and the resulting recoil threshold, then these results are within 20 or 30% of what our TRIM calculation, this melting point heuristics give you. And so there's some hope that despite all the hand waving, we're within, maybe 30 or 50% of the actual value we're using. So next on to color centers. So just let me show you this here. So this is a natural topaz, and this is the color a piece of the same topaz got after it was irradiated with gamma radiation. Okay, so you can see radiation changes color. That's why these things are called color centers. Same example here. I have forgotten what this is. This also could be calcium fluoride, I think. Unirradiated, irradiated. Okay, so there's a clear color change. And in an ionic crystal, the concept is very simple. An ionic crystal, for instance, sodium chloride, that's the salt you put on your French fries. If you have an N-ion vacancy, it traps an electron. This is shown here, right? You take out the N ions, you have a net positive charge as a result. And so then an electron which goes there gets trapped, and that's going to be quantum mechanics in the square well fundamentally, so you get distinct energy levels. As I said, this is often used to artificially change colors of gemstones. And what's now the neat thing is individual color centers can be seen in visible light by fluorescence spectroscopy. So this is shown here. So you have here the valence band, which in an insulator is full. You have the conduction band, which is empty in an insulator. You have this color transition. So these are the F-center energy levels. So you can shine in some light, lift this into the conduction band, and then it will fall back, not necessarily into the F-center itself, but can also fall back to the valence band. But in any case, you get back some light out. So, and you can see this. And this has been done for single color centers, for instance, with nitrogen vacancies and diamond. As you know, people are very interested in those as qubits. And the reason they're interested in qubits is because they have certain spin properties, which we don't need, okay? And I should say color centers have been observed in a really, really wide class of materials. So many things have that. So now, does this work for us? And so what's nice here, there's this 2019 paper by Mosbach et al. From the Weizmann Institute, which did the following. So they have here a monochromator to basically select the excitation wavelength. They have here their sample. And then they have another spectrograph to measure the fluorescence spectrum. And what's shown here are the results for, and so the trick now is they measure this before and after irradiation. Okay, so that they can irradiate the samples with neutrons and gammas. So they have taken here barium fluoride, and as you can see, there's a bump here at an excitation of 250 nanometers and an emission of 450 nanometers. After this has been irradiated with neutrons from a californium-252 source. Now, if you look at this same material irradiated with a 5 times higher dose of gamma rays at the same place, you have not formed any color centers. So the color centers at those wavelengths are selectively formed only by neutrons, that is by nuclear recoil events, and not by ionization events. And this is this intrinsic rejection of gamma ray backgrounds and beta backgrounds and alpha backgrounds we need for this to work. And this has been demonstrated also in sapphire, which is aluminum oxide, and lithium fluoride. And so that gives us a high degree of confidence that the fundamental physical concepts we need for this to work actually are in place. So what readout schemes do we have? And I need to speed up a little bit. So one is confocal microscopy, which has been used for nitrogen vacancy centers. And the idea is that you send in your excitation light through the microscope. You get the fluorescence light along the same light path. And you can do these nice images. The problem is you have to raster the whole volume 1 point at a time. So you get the locations of the defects, but you have only a tiny volume. Then this other paper here, which was one of the papers proposing this for dark matter, they proposed to use an optical fiber, and you basically measure the total fluorescence you get in the fiber. So you get a sizable imaging volume this way, but you get no location of the defect whatsoever. So if there are pre-existing defects, they're going to be a background, and you have to statistically subtract it, which may limit your sensitivity severely. What we found is there's this light sheet microscopy. So you basically, instead of shining the excitation light in through the same light path, then you read it out, you have a light path for the excitation light, which is orthogonal to the fluorescence light path. And in that way, instead of imaging a single point, I can image my whole field of view with, I don't know, the 10 megapixels or whatever my camera has. And so these methods really can image something like 50 to 100 cubic centimeters per day at sub-micron resolution. And this really was developed to do this here. This picture down here is an embryo of a zebrafish. And they basically want to monitor, for instance, how the nerves work and these things. So they really want to make movies of that at 25 frames a second. And that's why they need this high volume capability. The neat thing about these devices are they commercially available. So that makes that suitable technology. So now we come to the nuclear recoil threshold. And so this is really the crucial figure of merit for dark matter detectors and CEvNS detectors. And so what we see here is for the example of sodium iodide. So if I can resolve tracks with better than 1 nanometer, then I get the blue curve. So I get a very early turn on and maybe 20 or 30 electron volts. But if I only can do tracks with 2 nanometers, this orange dashed curve, my turn on point is more like at 100 electron volts. And if I go to vacancies, if I look at events which have at least one vacancy form, my turn on point is sort of 50 electron volts. And if I could do only cases where we have more than 2 vacancies, this would be 100 electron volts. The point is that you can achieve, by reading out this vacancy, sub 100 electron volt nuclear recoil thresholds, which so far have been otherwise only demonstrated by millikelvin cryogenic bolometers, which are sort of the high end of complicated detector technology, if you would like. I think I skipped this.
Can I ask a question about,
yes.
So vacancies greater than 1, vacancies greater than 2. What does 2 vacancies mean? Like anywhere in your material, or they have to have been produced by the same?
But by the same event, so that they're spatially close together. And so I would know that this was from the same event.
So how close should they be?
So in practice, I can answer that. If you go back to this figure here, they would be apart 1 or 2 nanometers.
I see. And this is happening because of the same nuclear recoil event, or
yes, because one event can make more than 1 vacancy, because if it has enough energy, it can kick out several.
Gotcha. Okay.
atoms.
Thank you.
That's the idea. Thanks. Good question. I'll skip this one. This is a technical detail, but we can talk about that if you're interested. Now let's move to the core piece. So for one part of the audience here, this is sort of the money plot. Dark matter detection. Turns out that lithium fluoride is a really great target for spin-dependent interactions, because both lithium and fluorine have an unpaired nuclear spin. Okay. And we're looking at spin-dependent interactions because spin-independent interactions, it's really hard to compete with germanium detectors. They're very good. And so what we're showing here is the dark matter limit you get from a 10 gram year exposure, 1 kilogram year exposure, 100 kilogram year exposure of lithium fluoride at a deep underground location. And we know from experience like PICO, for instance, which should be here, PICO 60, that neutron backgrounds seem to be negligible well into the 10 kilogram year exposure range. So you probably can go well below the 1 kilogram year before you have to worry about neutrons. And at 100 kilogram years in green, the neutrino fluor sits in. And you can see that below sort of 2 GeV, this is without competition. And at a 1 kilogram year exposure, you start actually to outperform any spin-dependent searches across all mass ranges. So that would be quite attractive. Then we also, of course, can look at SEVNS. SEVNS has not been observed at reactors yet. It's a very active field. There are many collaborations trying to do this. And what's shown here in this figure is the statistical uncertainty in the SEVNS cross-section you would achieve as a function of the background rate you have in the region of interest. And so here at the right above 10 to the 4, this is what you have at the surface. But with a little bit of shielding, this passive shield here is roughly 1 meter watt equivalent. So it's basically drowning this thing in a swimming pool 1 meter deep. You see that with 10 grams, I already can in a year achieve maybe at 7 or 8% detection. If I go to 100 grams, this would be a few percent. And at 1,000 grams, I would far be below 1% where flux systematics will dominate this. And this is a passive detector. This is really a 100-gram piece of salt in this case, which you deploy 20 meters from a reactor for a year. You take it back to your lab and you do the measurement there. And that's interesting for fundamental physics. It will allow you, as we discussed, a whole bunch of non-standard physics scenarios and BSM scenarios. And eventually, if you go into this range here, also could be useful test of reactor flux models for reactor neutrino emission. Now we can use this also for safeguards, and this is now sort of where we move sort of to the other part of the focus of interest of maybe the other part of the audience. You could use this to verify a shutdown of a reactor, and you want to verify this to make sure that no plutonium was produced. So the criterion here is that you want to, within 90 days, be able to put a limit better than 1 significant quantity, which is 8 kilograms for plutonium. In this figure, we show several candidate materials, again, as a function of the background rate. And you can see that these materials sort of cluster, and you see now here we have bands. These bands arise from a plus minus 20% variation of this threshold damage energy. So yes, it does make a difference, but it's not like if you are 5% lower, so you move off the plot. And so that's why we think that within the fidelity of our calculation, this is a fairly robust prediction. And you see this are different materials, and some of them do slightly better than others, but basically all of them go below 1 significant quantity at this sort of 10 to the minus 2 background events per day level, which again you can achieve as a 1 meter equivalent water shield, or a shallow borehole, which you basically can dig by hand. And this is at 20 meters from the reactor for 100-gram crystal for 90 days. And so that would allow you to use, so the scenario is you deploy this crystal, you let it sit there for 3 months, you take it back to your lab, and if you find no evidence of seventh events, you know the reactor hasn't been running and therefore could not produce plutonium. And you would have a limit on the reactor power, which makes sure that, so even if the reactor ran at low power, you would limit that the amount of plutonium which was produced is below 1 significant quantity. This is important because you can verify reactor shutdowns, and so you can verify the end of plutonium production. And for smaller reactors, you also can have a reactor which is running, but you could put a limit on reactor power and duration of operation, which is interesting for a very limited class of research reactors, but some exist. And so this would directly support non-proliferation. And so this is a photo of Haifa, and this again is the Hanford B reactor in all its glory. All right. So this is the neutrino part of the thing. But if you build a neutrino detector, we have been talking about neutrons so far as backgrounds. So what if you drop neutrinos and just look at the neutrons? The neutrons are much easier to detect. They're more plentiful, they interact more, they have more energy. What can we do with that? What I'd like to introduce to you, and I assume to the sort of SciSec audience, this is probably already known, but for the physics colleagues, this may be still fun, is nuclear disarmament verification. Fundamentally, the problem is how do you prove two objects are the same without revealing any other information about these objects? And this is the idea of the zero knowledge proof protocols. So I assume that Alice has 2 cups and she claims there's the same number of marbles in it, but she does not want you to count the marbles. Very importantly, she does not want to disclose how many marbles she has. And she also then offers 2 buckets of marbles, and she claims that the buckets also contain the same number of marbles. I mean, the buckets, not the buckets and the cups, right? Bucket and bucket, same number, cup and cup, same number. You are allowed, so Bob is allowed to randomly choose which bucket the cups are poured into. And if you count now the marbles in each bucket and you find the same number of marbles in each bucket, after the first game, you have a 50% chance or confidence that there were indeed the same number of marbles in the 2 cups. If you repeat this game after the 5th game, you're already at 95% confidence. And so you have learned nothing about the number of marbles, but you can be 95% sure that they're the same. And so zero knowledge proof is great if you want to prove that your object under test belongs to the same equivalence class as a template. And of course, we're not talking about marbles here, but nuclear warheads. And so this is an idea how this would look like. You have a neutron source, you have neutrons going through your warhead knockup, and then you have a detector area which can count these neutrons. And these detectors are what the cups, sorry, the neutrons coming through that test object are the cups, and the buckets here are the neutron detectors. So the host would preload these neutron detectors in a way that you get no image if you put a warhead in front of it, so that each detector has the same number of counts. And then you would analyze these detectors. For this to work, and this here is a proof of concept experimentally, they use superheated emulsion detectors. This is very much like the Pico detector. And so here you can see they use 7 pixels. And here comes your neutron beam. And these detectors need to be preloadable, so the buckets need to be able to be filled with marbles. The preload must be stable. You cannot have marbles running out, evaporating, anything like that. The host must be able to verify the preload, otherwise they disclose information to you. It has to be insensitive to gammas. It must be non-electronic, and it must be unspoofable. Otherwise, there's no trust in this exercise. And it turns out that our color center-based detectors check all these boxes, and MEV neutrons are much easier to detect than reactor 7s because they're MEV recoils and not electron volt recoils. So what do we expect the impact to be? Our detectors are non-spoofable because neutrino signal can be distinguished from neutrons by scaling with atomic mass, and you also can actually scan the pre-existing point defects, which you need to subtract them as a background in a 1-by-1 basis, not statistically. But of course, you also fingerprint detect the no pieces of glass or crystal have the same location and number of defects. Passive detectors of already 100 gram likely can be incorporated into safeguards operation without disruption. Our detectors would be the size of Hershey's bar, which is really not very much more inconvenient than the actual size of an IEA seal. The detector materials are commercially available. That's stuff here you can buy. You go to websites, and it's not even expensive. A piece like this here, which is sort of 10 by 2 by 2 centimeters, is a few $100. This is a light sheet microscope. You can buy them too. They start at 50,000, and the fancy ones go up to 250,000 or so, but nothing you have to develop. So to summarize, first of all, I'd like to thank my collaborators, Bernadette Coxwell and Apurva Gul. And I think we've shown that passive SEvNS detection based on color centers seems theoretically feasible based on detailed simulations. The resulting detector sizes and deployment footprints appear promising. No cryogenics. The detectors are less than 1 kilogram. They're fully passive. And you have, besides SEvNS, applications to dark matter detection, neutron detection. And so the next steps we're planning are, so the Princeton folks at the Plasma Lab and the Science and Global Security Program have indicated interest in exploring these detectors for the zero knowledge protocol they have developed. And Igor Jovanovic at the University of Michigan is interested in developing this technology for measuring radiation production in harsh environments, such as high-intensity laser metal interactions and pulsed power devices like at the National Ignition Facility. And we all happen to be within this consortium for monitoring technology and verification, which is an NNSA-supported consortium of 13 universities and the DU National Labs. And so that's a very natural framework for developing that technology. With that, I'd like to thank you for your attention. We'll be happy to take any questions you might have.
Okay, well, thanks very much for a very interesting talk. Oh, sorry.